This is our vorticity analysis over smooth cylindrical bodies presentation. So basically what we were trying to do was we were studying the flow over varying cylindrical sizes at both a high velocity and a low velocity test run. Our goal was to analyze and characterize the vortex formations coming off of each of these cylinders. And in order to do this, we utilized both analytical and numerical methods, including the particle image velocimetry. And we wanted to do this in order to understand the phenomena of vortex structures and the vortex street better.
So the materials that we used included 3 different cylindrical objects, and those were just PVC pipe, all varying diameter. And varying the diameter was important because we wanted to target different types of vortex structures behind it and see how that effect of increasing or decreasing the diameter would change this. Next, we had a 32-gallon tub, and this held our water, which served as our test bed that we would flow the cylinders through. And then after that, we have blue ink, and the blue ink served as kind of like a backdrop. We would put the blue ink in the water, mix it around, and it would give something that would highlight out the vortex structures inside the flow. And next, we had talcum powder, also referred to as baby powder. And that was just used to sprinkle on top of the flow. It's very important that the baby powder did not go into the water. It's just set on the top surface of the water and didn't break the surface tension. And that will also allow it with the blue ink as a good contrast to really highlight that vortex street. And then finally, we had the high-speed camera footage. We used was just a normal iPhone recording in slow motion, which is about 120 frames per second. So our methods, first we had our experimental setup and data collection. And so what we did, again, was take the talcum powder, baby powder, and sprinkle it on the top very slightly, make sure to get a uniform distribution of the baby powder across, and also make sure that the blue ink is uniformly mixed inside the flow before you did this. And then once that was finished, we took each cylinder and then inserted it into the flow and then moved it in a slow case and then a fast case through the tub. And what we were trying to target was about 0.1 meters per second and 0.2 meters per second, respectively. And we did this for both cylinders. And then next, once that was finished, then we could analyze our results. And we, taking high-speed footage, something like seen here, of the video, we could analyze and look at the vortices that form behind the cylinder, and taking into account like their frequency and number of vortices, we could find things like things that characterize this. So first, we found the velocity of each of the cylinders, and that was done taking the distance traveled, the known distance, which was about 17 inches across the tub, and then averaging how much time it took in the high-speed footage to go from the top to the bottom. And then we did this for about 5 times for each of the cases to get an average velocity. And then once we found that, we can do the Reynolds number calculation, and that is just found using the density of water, which is known, the dynamic viscosity, and the different diameter cylinders of the pipes, and as well as the velocity that we calculated. And then after that, we did the Struhal number, which was taking into account the vortex shedding frequency and the number of vortices, as I mentioned earlier. And then once we had both of those, we plotted the Reynolds number versus Struhal number, and this was to see if there was any correlation between the two. After we did a visual analysis of the flow, we then used PIV Lab to take the qualitative data of the video and then translate it into something that is more quantitative. And so what PIV Lab allows you to do is you can give it a video and you can break it up into frames. And so each of these frames, it'll look at these small particulates in the flow, that was our baby powder, and then go from frame to frame. And once you calibrate it, it'll see how fast it'll move between frames. And so this can be characterized into a vector field for the velocity, and then you can also relate it to a heat map, which is the vortex structure and vorticity that you can see right here, and that'll let you know and then how strong the vortices are and where they are. And once that was done, you can also calculate vorticity using a bounded area and a calculation tab inside of PIV Lab.
So on to the results. First, there's the results of the visual analysis. And you can see through our calculations, we came to the various Reynolds number, which went from about 2,300 to about 8,100. And our Struhall numbers remain pretty constant around 0.2, which agrees with the literature. We do have Struhall numbers that are a little bit higher than expected, but that can come from the inconsistencies in the velocity or the kind of shortness of the trial period. And these are our flow velocities, which were used to calculate both of these numbers. And those are the formulas that we used on the graph. And now for the results of the PIV lab analysis. So for the small cylinder case, here you have the fast case on the left and the slow case on the right. And the parameters of each below. For this fast case, there were 4 vortices that completely separated. So those are the ones that included. And you can see that it has alternating values that are about equal, as well as with the slow case. The first vortex on the slow case right here was considerably weaker than the rest of them, but the rest do hold up to what we expected to see. And these numbers were calculated by taking a circular area around each vortex, and PIV lab was able to use the vector field to calculate the vortex strength.
So next, after the small cylinder, we did the medium cylinder, and this is the slow case for the medium cylinder where you can see the PIV lab results on the left, and then our calculated vortex parameters on this table. And that's for each of the vortices that are shown in the graph. And from that, things that pop out are that both vortices seem to have very similar strengths in magnitude. The only difference between them is that they are opposite, and that is because they are spinning in opposite directions. So like as a cylinder moves through a vortex, or 2 vortices will be created in opposite directions and shed. And this is due to a von Karman vortex tree developing after the cylinder, which essentially just means a repeating pattern of alternating vortex strengths. And once the slow case was done, then we did a fast case for the medium cylinder where you can again see the PIV lab results and the same parameters, just different calculations. And so again, similar to the slow case, we had vortex strengths that were approximately the same. And the only thing that was different from them is the negative sign that was on the right vortice.
So for the large cylinder, we see the same trends as from both the small cylinder and the medium cylinder, that being that the vortex strength for the magnitudes of both the vortex on the right side and the vortex on the left are of similar magnitude, but that they are in opposite direction because once again, they spin in opposite directions. The same can be seen here in the high velocity for that large cylinder. And we see here again that the vortex strength on the higher velocity is greater than that of the lower velocity for the same size cylinder. So ultimately, we were able to find our Struhall number and our Reynolds numbers, which may not have been exactly perfect, but they followed the trends we were expecting to see based on our literature review. We were also able to find a correlation between our Reynolds number and our vortex strength, which can be seen in the graph on the bottom left. It shows that as Reynolds number increases, the vortex strength should also increase. We obviously have a few outliers, which we attribute to inconsistencies in the area we did our experiment that were out of our control, as well as possible technical and human error. So in conclusion, our results showed exactly what we were looking for, that the Struhall number would be around 0.2 and that our Reynolds numbers would be between 2,300 and 8,100. Seeing a constant Struhall number indicates the predictable vortex shedding in laminar boundary layer, which is exactly what we wanted to see. Our experimental methodology using the video and the PIV lab produced reliable data following the trends in literature, which once again is good. And we think that in the future, use of PIV lab would be a good way to look at surface roughness on other flows.